Thank you. Right, we're gonna get started. So for today, for this week, so the plan for this week is we're gonna finish talking about the MCMC diagnostics today, as well as go through as much as the paper discussion that we can. And then on Wednesday, if we need to do a little discussion, we can continue. And then I said that Wednesday we're gonna offer some lab help in terms of figuring out that particular homework question, which is the second question of homework 5. So I would say before Wednesday, you should at least, so there's 2 parts of it. One part is about the derivation of the Gibbs sampler, and the second part is how to do the Gibbs sampler. Okay, so right, so I was sending a reminder email about this, the plan for Wednesday, but the goal is finish as much as the paper discussion by today. And then on Wednesday, if we need to spend some more time, we'll do it. And then most of the time, we'll talk about that particular methods itself for that particular question. So that relates to something called latent class modeling. So on Wednesday, I will also introduce part of that as an introduction to it. And then, but the whole context is going to be under that particular homework question. So I would say definitely go check it out, and you can do some derivation, and then it's going to be related to it's going to be related to the particular example that we have seen in the lecture 8. So I will bring this up now, give you some hint of it, and then we're going to start today's lecture. All right, so last time we've been doing this diagnostics for a while. So the first thing that I want to talk about is this. So we talked about the particular idea of doing, adding one extra variable over here. So if you remember, we're looking at a mixture model. You have 3 components. So this is the truth. Oops. This is the truth, all right? And then in order to start a Gibbs sampler to sample this, we introduced an idea of now thinking about one extra parameter, which is the indicator telling you which component you should sample from, okay? So this will be the indicator, and then given the indicator, you know that you should sample from this normal for the first case, second normal for the second case, and third normal for the third case. So this was the setup, and what we were trying to do with the MCMC is this particular full conditional. So I'm highlighting this first just to bring you back from the weekend about the idea that we talked about last week of how we're doing the Gibbs sampler, but also this is going to be related to that particular homework question that I'm asking you to do early. So on Wednesday we can talk about it. So we're gonna just right now just look at it again. So the full conditional, so right now what the distribution has, we're trying to get the joint of mu and delta given y. Okay? So this is the joint posterior that we're trying to do. So we know that in order to do a Gibbs sampler, you have 2 full conditional to come up with, right? The first one is mu given everything, right? The second one is delta given everything. Okay? So the mu given everything, since now the everything includes the indicator function, it's pretty straightforward. You have 3 kinds, right? If it's the first component, it's going to be the first normal, second component, second normal, third component, third normal. So as straightforward as it is. But if you're trying to come up with the full conditional for delta given mu, this is something new that we introduced the first time last time. And this idea definitely not just restricted to this particular problem. It's possible to do for many other contexts. And the general context of this is called the latent class, or like sometimes we just use a latent variable modeling. Okay. So the name probably tells you something about it already. It's latent, it's underneath. It's something that you don't observe, but you're trying to introduce it into the modeling to, say, facilitate the sampling or facilitate the computation. So let's think about this. This delta that we introduced as an indicator can really be think of it as a latent class indicator in some way, right? Suppose you don't observe this delta at all. We only observe the y. But if you introduce this delta, thinking of it as some latent variable telling you which component you sample from, then it is really like a latent class idea that given different latent class indicator, I'm gonna sample from a different normal. So this is the general idea. So the challenge, of course, right now is how to get a full conditional for this latent class indicator. Okay? So the idea that we were doing back then, I show this really quick. And I still think you should go back to think about the derivation of why this is the case. But right now, let's just look at it one more time together, because this again is related to homework 5, the second question that I said is a bit challenging. So in order to decide the full conditional for this latent class, we're using Bayes' theorem. So look at this. This is trying to determine the probability of delta equals to D. D is 1, 2, 3, 1 or 2 or 3, given the mean and the data. So in order to determine, you can think of it as which latent class it comes from or which component I should sample from. It's really evaluating a Bayes theorem in the sense that on the top, I'm looking at the joint probability of the data coming from that particular latent class. In the bottom, I'm summing up all of the possibilities. Okay? So on the top, this is the density. Density of the particular y evaluated as a normal model because that's what we assume in the first place. So we're having this from a 3-component. So this is evaluating the data at the D component. Okay? So this is D norm, so that's why it's using the density, D norm in R, to estimate that particular density. And then multiply, you can think of this as some kind of prior over there. And down here, I'm doing it for D prime, and D prime goes from 1 to 3. Okay? So on the top, I'm looking at the probability coming from that particular component or latent class. In the bottom, I'm summing up all of them. And then you can think of this as a normalizing constant, right? Usually we don't compute it when we're doing, like, say, conjugate computation. But over here, since we're determining which one we should sample from, we need to compute all of them, and the computation is not that bad because you're going to use D norm to estimate the likelihood function, and the rest is related to the prior idea. Okay, so I'm highlighting this again because you will see that you will use the same idea soon if you're working on the second problem of homework 5. Okay, once you have mixture, once you have different components, this is actually a very popular idea, and then there's many variations, many extensions of this type of modeling out there. Okay, so yeah, so I would say after class today, go back to look at that particular data analysis question. That's homework 5, question 2. The data set is uploaded on Moodle, so you can load it and then try different things. But of course, in order to make that work, you first need to derive the full conditional, like what we're doing here, but with a different context, and then figure out how to sample it, how to do the coding. So it's 2 parts. Each part is not that trivial. So definitely start early, and on Wednesday, we're gonna come together to look at it as well. Okay? All right, so, all right, but this is also, I mean, I want to go over it because this was the setup that we were doing back then. So remember, so let me just recap what we did before. So this was the model itself, and then we can actually do independent Monte Carlo sampling by doing this delta thing. So this will be a nicely looking Monte Carlo density that should be the truth. okay? Because we know that we're sampling from 3 different components. First one is 45% chance, middle one is 10%, last one is 45%. So the density looks like the truth, and that's Monte Carlo approximation for only 1,000 draws. And if we're gonna do Markov chain Monte Carlo, the Gibbs sampling, this was the full conditional for both cases. And this is how you're gonna, so this is the example that I gave. If you start with the starting value -6 and delta is 1, then this will be the sampling of 1,000 draws. So definitely not good, too much stuck into the first component, right? Too little in the second and the third, especially the third. So we were trying to use this example to figure out what went wrong. So we went through several aspects of this. So the first one is trace plot. Trace plot, this is for Monte Carlo. This is what it should look like, right? You have 3 clusters. The first and the third should be more concentrated because you have 45% chance for each, while in the middle it's less dense because it's only about 10%. So this is the Monte Carlo, looks good. However, once you move to the Gibbs, we saw that it's definitely not good, not only from the histogram that we saw before. This particular plot called trace plot also tells you not good enough. So I think last time we were saying that even though you start from -6, it jumps into part of the parameter space really fast, but it got stuck over there, right? So it was around -3 for a while, for the majority of the time. And then for some reason, it came to the other part, which is good, but it only stayed there for a little bit and then come back. So too much concentration on the first component, very little on the second, and a little bit on the third. But even just looking at this, you might guess that we should have run it longer, right? Because this is only 1,000 draws. If you run it longer, then the chain probably will be able to explore the parameter space much better. Okay. So this, again, trace plot is one of the first things that you should check how your chain is doing. Okay, so this is the example. And we talked about stationary and stickiness. Stationary meaning that trying to converge the target distribution. And then stickiness is how like the autocorrelation function is doing in some sense. We don't want it to be too sticky because all of the draws are too dependent from each other. We need to get rid of the dependence. Okay, so this is autocorrelation function with the Monte Carlo. Looks really good. Only the first one is 1 because that's with yourself. And then from the second draw, it's just independent. Everything drops. Okay, so this is what it should look like. So this is the Monte Carlo, but the MCMC, the Gibbs, was pretty bad. We saw that. And then this is the ACF plots with the Gibbs sampler. And you see that, because this is telling you the autocorrelation function. So with itself is 1, that makes sense. But then with the next draw, it's still very high. And even if you get the 30th draw, it's pretty high, right? So this indicates that all of the draws are too dependent from each other. We need to do a lot of thinning, meaning that you only save every, I don't know, in this case, maybe every 100 draws. Okay? So this is another aspect of it. And then, so last time we end around here, and I showed a couple of things that you can do. So we're gonna keep talking about this, and then I think in the process, I'm gonna start referencing to the particular paper, because I think one paragraph actually talked about all of the diagnostics that you can do. But again, the explaining Gibbs sampler paper was very early, just right after it got developed. So you will see that in that particular, so let me actually show you what it is. So if you can bring out the paper, you will see that it's section 5.1, okay? It's called Detecting Convergence. It's only a couple of paragraphs, I think. Yeah, 2 paragraphs actually. And then back then, they started talking about some of the ideas, but obviously so right now on the screen, all of those diagnostic functions are actually well developed, so we can just use it. But back then, when this paper was written, there were just some of them were developed, some of them were still underway. So you will see that like how things change after so many years. Okay, so 5.1, section 5.1, detecting convergence. That's the diagnostics that we're actually talking about so far. All right, but you can go back to read it. I'm just saying that at that time, all of those diagnostics were not well developed, but right now things are much more settled down. All right, so trace plot, we have seen it before. Of course, it's showing you the progress of the chain over time, okay? The ideal trace plot should have a lot of movement around the entire sample space and also from iteration to iteration, but not a lot of stickiness, meaning that you shouldn't stick in a while, like in a region for so long and then all of a sudden jump to the other. Also, trace plot should be able to tell you whether the sampler has not converged, okay? Yeah, but and in that case, you should run it longer. This is the case where we have seen earlier. But of course, all of those diagnostics can only tell you bad things that happen. It can never tell you that it's just perfect already, okay? Because there's always the chance that you might need to run it longer, or you might need to start using a different sampler, et cetera, et cetera. So this, like all of the diagnostics, I mean, that's why you call it diagnostics. It's not telling that it's good, it's just telling you that nothing is bad. So this, in that case, is kind of similar to what we have done with the posterior predictive checks, remember? We're doing the PP posterior predictive checks just to sample or like generate new data from the model. And then we can only tell that the model is not good because some of the statistics that you're returning from the generated ones and the original ones, if they're far away from each other, that tells you it's not good enough, but it's never gonna tell you that that's a good model. Okay, so diagnostics over here kind of works in the same sense. So yeah, so that's trace plot, and then in order to use it, you will also, let's see, another thing is the autocorrelation functions, and then we have seen some of the plots already, but the goal, again, just to restate it, the goal is to figure out whether we have independent Monte Carlo draws. And because we're doing it from Markov chain Monte Carlo where things are dependent, we're gonna need to make sure that we don't have we don't have too big autocorrelation, because that means the chain is not mixing well. So we need to either do thinning or come up with something else. All right, so something related to that idea, I think that's where I stopped last time, is the effective sample size. So the effective sample size, think about the name. So sample size here is not talking about the data sample, okay? Here is talking about, say now we have run the MCMC chain for 1,000 times, and we know that it's sticky. We know that it's dependent draws. And we want to figure out, oh, so how does it, like how much does it mean for this 1,000 draws to represent like the sample size of independent draws? Okay, so that's why I say, look at over here, the code. So we're all using the CODA library, and then you turn, first of all, you turn the particular particular vector into an MCMC object, and then you use the function called effective size on the particular thing, and then you will be able to return effective size. So this is telling us down here, you see the last paragraph over here, the precision, which is telling you like how many copies of independent draws actually it means to have the particular 1,000 draws of the MCMC, is actually only as good as taking 3 independent samples. Okay, so that's what effective sample size means. Okay, we want to have large enough effective sample size, because think about it, MCMC, we run it for so long, but a lot of draws is not going to be useful. We're going to have to drop them. Okay, so this effective size, this function is actually giving you a sense of, okay, now you have run it so long, how useful it is, and it's defined to be effective sample size. So this obviously is not good, even though you have run it for 1,000 times, it's only as good as 3. The rule of thumb, I think you should at least have 100 effective sample size. Okay, rule of thumb, but of course that might be, say in this case, you probably have to run it much longer. Might not be a good resource, like you might not have enough resources, but the rule of thumb of how many effective sample size you need to have is usually about 100. And you can think of that 100. So back then, remember in the MC approximation, Monte Carlo approximation, we were doing like capital S to be 1,000 or 10,000. And we're summarizing using all of those. So here, the effective sample size will be that S number. Okay, so back then, because everything is independent and computing is so easy, so you can get 1,000, 10,000 very efficiently, while here you only get 3, you obviously need more, because otherwise you're only summarizing based on 3 drops. Yes, Eli?
So does the MCMC effective sample size test use autocorrelation function?
Yeah, so here, I think so. So on the top, I did include, in the middle part, I did include the formula as how that is defined. Yeah, so I think, yeah, you actually need to take into account multiple things, and then obviously autocorrelation will be one of them. Yeah.
The other question I was going to ask is autocorrelation for a linear relationship between a previous straw and the next straw? Or what if there's some sort of like non-quadratic or cubic relationship?
Good point. Yeah. So actually, yeah, maybe I should go back. Let me see if I have anything about that. But so Eli's point is a good point, because whether, and then that makes me actually want to check if the autocorrelation is indeed only looking at linear correlation. I guess, yeah, I don't think I know the answer at the moment. But I do think they should take into account not only that, but all of the other possible ones. But again, not every measure is perfect. This one is trying to give you this variation of the MCMC in terms of the variation of the Monte Carlo, and then divided by the effective sample size. So per that particular question, I think I need to go back to check it. But the general idea is, I think in order to come up with a good measure of the effective sample size, you do need to take care of the autocorrelation. But I think definitely something else as well. Yeah. Okay. All right. So yeah. So the general idea is that if you have highly correlated chains, even if you run it for so long, the effective sample size can be small. Okay. So if it is small, you should run it longer to get accurate summary of the posterior distribution. All right. A third diagnostic over here, which actually will be very intuitive. I think the idea itself, and you'll notice that it's not something very fancy. So let me tell you like the general idea first, and then tell you what they're doing. So the Geweke in 1992, they also proposed a new convergence diagnostic, and they're only looking at, so think about a chain. You start a chain. If the chain is converged and then you want to, like if the chain is good, like mixing very well, explore the entire thing, you would imagine that the first, saying here, by default, the first 10% of the chain and the last 50% of the chain after burn-in shouldn't be that very different from each other, right? If you have done it well in a good way. If the chain is mixing well, if you, after the burn-in, if you take the first 10% of all of the drops and the last 50% of all of the drops, the means in particular, if you try to do it, so here, what they did is actually just a two-tailed z-scores, like two sample tests in the frequentist sense. They're looking at the first 10% and the last 50% and then test the mean, if the means are significantly different from each other. So that's what this Geweke diagnostic is doing. You can think of it as 10% of the samples from the beginning and 50% of the samples from the end. And you treat these two as two different samples and you're testing the mean. Okay, so this is what this Geweke diagnostic is doing. So it's pretty much just give you a two-tailed z-scores. So based on what you have learned before, I think hopefully you know about like testing two different sample means in the frequentist sense. So that's what the Geweke diagnostic. So here, the code is just called geweke.diag. And then because it's a two-tailed z-scores, if the z-scores are really large or very small, say like absolute values beyond 2, it either is above +2 or smaller than -2, that indicates poor mixing. Okay, that indicates that these two samples that you come up with are very far from each other. Okay, so here there's so again, rule of thumb is absolute value should be below 2. If it's above 2, it suggests poor mixing. And in this particular case, it's actually in that aspect, it's not too bad, right? And if you think about, this is kind of ironic in some sense. So if you go back to, look at this. Yeah, it's somehow like the chain started around -3, and then for a while goes somewhere else and then come back. So a chain like this maybe wouldn't show badly in the Geweke diagnostic, but you see that if you look at other measures, it's not good. So what I was saying that if you look at this, the first, say 50% or like whatever percent, the thing is, I was trying to say that it starts, so this exploration, the beginning and the end are kind of concentrated around -3, right? But from the trace plot, we know that this is not good mixing. But by chance, the Geweke diagnostic didn't test it, okay? So again, any measure cannot tell you that it's good, it can only tell you that it's bad. But usually a bad chain gonna be bad in many measures. So I don't think you will go wrong, but I just want to show you that for this particular case, because you might be wondering, well, the Geweke wasn't that bad, it's only -1, right? Yeah, but it's, I think, by chance in this particular case, okay? So default is first 10% and last 50%, but you can change things, okay, based on your preference, but usually I think it will be the default, and that's the Geweke diagnostic, nothing fancy, and I think the idea is very beautiful, it's just very straightforward. I now have a chain, what I'm gonna do. Oh, this is after burn-in, yeah, right. So again, this particular example that I show you with this, I mean, we're not doing any burning anyway, so this is just very crude example of all of the measures, how they're doing, or how you can make them work. But I just want to show you that that's why. So I think the particular, so you should do it after burn-in, maybe I should say that. But for right now, I didn't do it. I just want to show you how different measures work, and in particular for that particular example. All right, so this one, Gelman-Rubin Diagnostic, is also very straightforward, I think. So let me explain like the general idea and then go into the detail. So this is along the same line as running multiple chains. Okay, so this, I think, you have read this paper, you realize that back then, or like even now, some people try to stick to that idea that I'm not running a super long chain, I'm trying to run multiples and then only save the last one in order to get independent draws. So the thing is, how we will be able to test if they're still well mixing in some sense. I'm generating m different chains and I'm saving the last one. How am I be able to make sure that this is working well? Saying that we start at different values, maybe the end are around the same values, but all of those values fully exploring the entire parameter space. Okay, so this is what we're trying to figure out. And this is what Gelman-Rubin Diagnostic is doing, is looking at multiple chains and then looking at whether all of the values, like all of the draws are well, like really spread out relative to the posterior distribution to ensure that the chains are not stuck in the same region. Okay, so let me show you like the general idea. It's not, so if you have done anything like ANOVA before, this is related to ANOVA. I mean, I think in statistics, many ideas, like the fundamental ideas is actually very similar. So over here, if you're gonna do multiple chains, a natural question to ask is, say now I have m different chains. If I can compare the variation within each chain and across each chain, if the ratio or like if the variation between those, like between and within are in certain range, I will be able to tell that all of the chains are doing similar stuff, right? So this is a general idea. But again, we won't go into detail because you notice that in R is just one line code that's gonna tell you what the result is. But I want to give you the intuition of what this Gelman-Rubin diagnostic is doing, okay? So it's similar to like analysis variance, so that's what I was asking if you have done any ANOVA type of stuff. And so say here, like capital B is defined to be the between variance, okay? Between variance, so it's looking at, so this is too much detail, so I don't want to go into it, but the general idea is you get the between variance, you get within variance, and then you're gonna compare them, okay? The between is talking about between different chains. The within is talking about within a particular chain, but you have m different chains together, okay? So that's another way that you can measure it. So rule of thumb, it should be not that far from 1, okay? So
like once you do this Gelman, so here, if you run multiple chains and then use this particular command, you'll be able to get the diagnostic. And then the general idea is that you shouldn't be far from one. If it's far from one, suggests lack of convergence. And then, so here, again, rule of thumb is 1, whether 2.206 is too far or too low. Again, I would say definitely for most of the chains that you're doing, you should check all of the diagnostics, and then the altogether is telling you the picture, but not just one of them. Okay, say the Geweke earlier didn't flag it, but obviously looking at the trace plot, obviously looking at some others, it wasn't good enough for this particular chain that we did. And then Gelman-Rubin is doing this scale reduction factor. Okay? Yeah. All right, yeah, so with all of this, pretty much diagnostic cannot guarantee that the chain has converged, can only indicate that it has not converged. Solutions, we talked about this before, you do burn in, you do run it longer, you thin it even more, meaning that you save even more draws, like larger number of draws apart from each other. And then also, this is like the second bullet point over here. You probably have seen this in frequentist analysis before. You standardize variables, okay, just to get rid of correlations. So like regression, a lot of times people are going to standardize it, and this you can do that here as well. Even though I personally haven't seen much of that, but maybe I think I'm just ignorant. I don't know about the other aspect of this. You can also reparameterize models to reduce correlations among parameters. And then also, so the last one here will be like add auxiliary variables or like block some variables together. So this will be more advanced techniques that we won't cover in our class. But MCMC, like Markov chain Monte Carlo, like doing all of the convergence, the checks itself is a big research area itself. Imagine a bunch of people actually were trying to figure out how to come up with better sampling schemes, better ways to evaluate things. So it is itself a research area. So if you're interested, say, even though I don't think I list any paper for a project in that area, but if you're curious about all of this, feel free to explore, to read one of those papers out there if this is more of your interest. Okay. All right, cool. So this is what I want to talk about the diagnostics. You'll realize that in the end of the day, you're just using this CODA package to ask it to do all of that for you. But still, I think each of these measures is still very intuitive. I would like you to think through them and then get a sense of what would be a well-mixing chain and what would be the problems when you see like a trace plot. What would be the problem that you see autocorrelation function, et cetera, et cetera. So the general idea is not that hard, but of course, each of the measure was developed based on certain statistic properties of things. So, and those things, some are more advanced, some are not. Say like ANOVA, you have done that before, then the Gelman-Rubin shouldn't be that far away from it. You should be able to understand roughly the idea. And then autocorrelation, the plot itself is so straightforward to see, I think. Once you plot it, you'll realize that, oh, it's too much autocorrelation, I have to do more thinning, et cetera, et cetera. So I would say, so this example, I used it just directly from the textbook, because I think it's nice, not only just telling you how to do a Gibbs sampler, but also like segue to the idea of latent class modeling. You have mixture, you have multiple components with different probabilities, how you're gonna do the sampling, okay? But of course, you will be able to find other examples in terms of evaluating the MCMC diagnostics, which I think pretty much from now on, all of the samplers that we will do in order to do analysis, you're required to test all of the diagnostics, okay? All right, so I think that's what I want to talk about with the diagnostics. So pretty much with Gibbs sampler, we talked about the mechanics and then talked about the diagnostics, but all of them are actually all together anyway. So I now want to turn to this paper, and I appreciate that pretty much every one of you make comments on Moodle, and obviously some questions got more attention than the others, which is nice. So I guess we will be able to have a very, let me bring up. Yeah, so I just prepared like some basic slides with the questions that I have, but we're gonna go through them either one by one or in the order that you would like to do. I think certainly some, like I said, some questions got more attention than the others. Maybe those are relatively easier, or maybe there are just like so many different information in those better received questions. But before I show the questions one by one, I would like to ask if anyone just like some general idea or general comments about this paper. Do you think it's hard to read, or based on, there are multiple sections, some sections are easier, some sections are harder, and yeah, maybe just share your feelings about this paper, like what is the logic flow, how much, like which part you don't like, which part you like, and whether you think it's doing a good job explaining all of the definitions and ideas. Is it doing a good job about designing simulation studies, et cetera, et cetera? And yeah, I guess we can spend 2 minutes just in smaller groups so you can talk to your neighbors about it, and then we're gonna bring back as a whole class about this, okay?
Sure. Yeah. I thought in general, I think it was like somewhere in the middle there. I try to answer it. When I said so number 4 was try to find what's the best show that they can say so the idea so I said that the most important thing here is like the whole equation. The only variables are the two conditionals, and then the marginal value is some other. I said that is good. We said the same thing that marginal source. So that takes care of this. Just using like the general principles of probability to say because we don't know and just say MCMC so instead in this case we're saying that there is some relationship between times some other that's like when I said this because it obtained starting just by these guys. Right. Right. And I don't quite understand the words like this. T is a value that you're using the function for the marginal x. You're evaluating it as a value. My guess is that that's the sort of like previous values that the market gives to. And then I don't understand why. So you take a leap on some, sort of take it out of this here, and then you don't do anything to simulate that. So I don't exactly understand where that is. Yeah, the question is, oh, you mean like
There's
because if you theoretically you could do starting value just by taking some the last value that would be the same as the equation.
if it's not said,
It's probably what it is. Probably right. And you might be able to get having a larger sample size is also so you might the trade-off for the smaller, more independent samples might be not. Right. The other thing that I was thinking about is I sort of was uneasy at first the idea of like, how can you just get rid of the dependence? Like, it has to be, if it's dependent, it's dependent, there's no. So I was thinking about the way that computers calculate the numbers to begin with is sort of not actually independent. It uses these algorithms that have like a scheme. Right. So that was something I was thinking about. Is that I guess really what the Gibbs network is doing is it's approximating the same thing your computer does when you sample that's what so I guess it is something that we just accept if you get rid of the notion values divided by infinity. I'm thinking about trying to do this just proposing something that like I did that with the interesting and I have a hard time so I'm working on that on basically suggesting possibility of like yeah. Yeah. That's totally cool. Basically, the idea is to take something like some sample, let's say 1,000, and you can calculate from your data how much each observation is, because that's what your density is. So then you just draw a new random, and then you calculate the mean, and you do that about.
All right. I guess we can like discuss a few questions and break into to groups again, because even though, so when I came up with those questions, I was just looking at section by section. But I think now looking at it, obviously, some section, like some questions are more general than the others. So I would say if we want, we can start with question 1 and 5 and 6, because those are the things mostly related to what we do, what we have done in class. Okay, talk about different ways to do a Gibbs sampling, talk about like advantages and disadvantages of each of those ways, and then, so that will be 1 and 6. And then 5 is talking about how you can illustrate that idea with working K parameters, which we actually talked about in class. But also right before this, if anyone wants to talk about the paper in general, feel free to do that as well. So just speak up. I have the directional mic over here, so should be able to record most of the voices. So anyone? People are writing long paragraphs on Moodle, so should be able to talk about. I think many of the like answers are really well written. Like the logic, everything was really nice. Any idea? And if you have extra questions from here, so I do actually have some extra questions. I think most of the examples that they did, they only have K equals to 15 or even less. I mean, each chain, they only run it for 15 times. It's probably not a good idea. It's probably too short. But there are other stuff that you want. Yeah, I mean, those were something that I thought about, but I didn't ended up writing it in the reading guide. But anything else you want to talk about or directly address 1, 5, and 6, feel free. Yes, Eli?
Change for K times. Do they get their starting value just by taking some random, like a random draw? Or
Yeah. So one of the remote students actually put that. So the question is, you know, the same value?